So I want to talk to you today a little bit about some interactions that we've seen between 2D halide perovskite materials and methylamine vapor. So we're interested in the structural tunability of halide perovskites for a number of reasons, right? Going from the pure 3D perovskite to a layered 2D structure. People have seen, a number of people now in the literature have seen stability gains for that. It can reduce moisture sensitivity to have one of these long chain organic cations in the structure. The improvement mechanism is, I think, still somewhat unknown. I think we know some things about it. We see increased hydrophobicity, things like that, but the exact interactions between these 2D chains and the perovskite, kind of the lead halide sheets, are still somewhat unclear. On the other hand, we're interested in looking at some of these structures for switchable windows, kind of a new idea pioneered really by Lance Wheeler. So this is some work that Lance over at NREL did, where he looked at MAPI and saw that in the presence of methylamine gas, he could actually intercalate and deintercalate methylamine and get a color change from clear to dark. The idea being maybe we could design a color switchable window where we could go from a window to a solar cell on demand. There are some pretty severe morphological changes when we do this over a lot of cycles. So one of the ideas is perhaps a 2D structured or a mixed 2D, 3D structure will allow this intercalation, deintercalation of methylamine more reproducibly. The goals of our project generally were to evaluate the interactions between different azoite organic spacers and the lead halide sheets in 2D perovskites. So we did this by exposing films with one of these three different organic spacers, EA, PEA, and 4-fluoro-PEA. And one of the really interesting findings that we saw is when we took PEA, it's maybe most clear here, PEA and 4-fluoro-PEA, what we see initially is an intercalation of methylamine. The methylamine deintercalates, but some of it still remains in the film. So we actually get the formation of a mixed phase, like this here, where we have what we would call an N=2 phase, where we have two layers of the perovskite sheets. Methylamine is in there, and then the PEA on the outside. So we go from an N=1, where we're pure PEA, to this mixed 2D, 3D N=2 phase. And we see that for both PEA and 4-fluoro-PEA. For EA, ethyl ammonium, we actually see from our absorption spectra, it looks like we might be having the formation of some almost like a MAPI phase. We don't see strong evidence for that in X-ray diffraction. We're still working on reproducing some of these results and getting a little bit clearer picture of what's happening with EA. But we definitely don't see the transition from the N=1 ethyl ammonium lead iodide to an N=2 phase. So that's kind of an interesting thing where we don't seem to have this happening more generally. So there is some dependence on the organic cation. We're looking at now more organic cations and trying to tease out a little bit better what some of these interactions look like. I think one of the interesting things is we're seeing a preferential formation of the N=2 material over and above N=1 or N greater than 2 upon MA exposure. So I think this yields some insight into the hierarchical structures that people are seeing in 2D, 3D perovskites, where we have regions of pure 3D and also other regions of low dimensional materials. So we're looking still at exploring other A-site cations, improving the design rules of mixed 2D, 3D halide perovskites. Thank you.